How we doing, guys? Welcome to the video. This video is section 11D, motion in a vertical circle. So we're on page 203. We're going to look at questions 1, 4 and 5. So up to now we've been looking at motion in a circle and a horizontal circle. And if you have something moving in a horizontal circle like that, the upward forces and the downward forces have to be equal because the object moving in a circle is neither accelerating upwards or downwards. What we have now is motion in a vertical circle, so like this. Now you've got changes in the forces as you move up and down the circle. So that equation, that condition that we've been able to use up to now, we've lost. In its place, we're going to use the rule, the law of conservation of energy. So conservation of mechanical energy, the initial kinetic energy plus the initial potential energy is the same as the final kinetic energy and the final potential energy when added together. So we've met this in other circumstances already. So probably the easiest way to see how to do these is to just dive into one. The other rule we're going to stick with is that our inward forces are what cause us to move in a circle. So they are our centripetal forces. And while we still may occasionally see this one, m omega squared r, we're going to see mv squared r a whole lot more in this chapter, or in this section. So question 1, it says a particle P hangs freely from a point O by means of a light inextensible string of length L. The particle is projected horizontally with initial velocity √3 gl. Show that the string will become slack when the line OP makes an angle cos inverse 1/3 with the upwards vertical. So let's just sketch that out so we know what we're looking at. Okay. Things moving in a circle, that's down. Okay, gravity is acting downwards there. There's the center of the circle P, and there's O. Okay, so this is maybe swinging a weight on a string or something like that. We're going to project O either way. These problems are all symmetric, whether you go left or right, it doesn't matter. With velocity, an initial velocity of √3 gl. And the question is, show that when it gets up here, so that this angle here is, I'm going to call it alpha, but cos alpha we know is 1/3. Okay, so that this angle is cos inverse 1/3, that the string will have gone slack. So first of all, for our potential energy equation, we're going to need how high it is up there. So I'm going to draw another triangle here. They've used L for the radius, so I'll just mark that in. The length of the string is the radius, so that's L. This will be L along here as well, okay? So if I redraw that triangle, you've got L along here, and if that angle is alpha, then this one is alpha as well, okay? Because they are alternate angles on parallel lines. Which means this length here, which is part of what we're interested in, we remember are trying to find this height. Okay, well that's going to be the length of the string plus whatever this length here is, and that length there is L cos alpha. So we know that to be 1/3, so that's 1/3 of L. So our height at the start of this problem is L plus 1/3 L, and that's 4/3 L. Now, as the thing moves around, I'm going to define this angle here. Now, I'm going to say alpha is a variable, so specifically when we get to that point they've asked us about, we know that the height is √L. Well, let's call this theta actually. Okay, so that angle there, that angle there is 180 minus alpha. Okay, we'll leave it at that. However, what I'm going to be interested in just initially is as the rope swings up. Okay, so there's its starting position. When it gets to here, okay, this angle here, I'm going to call theta. And at our ultimate stage, theta becomes this 180 minus alpha. What are the forces acting here? Well, you've got tension acting inwards. That's what allows it to move in a circle. And you've got weight acting downwards, mg. Okay, always, by the way, put your mg to the left because you're going to resolve to the right along the same direction as the tension. That angle there is theta as well, same as this angle up here. So this is really common that you'll have to resolve weight and you'll say that's mg cos theta. There's an mg sine theta acting in this direction as well. but it doesn't crop up in the calculations very often. mg cos theta will. So our first equation now for conservation of energy says that a half m times u squared, well, the u is the square root of 3gl, so u squared is 3gl, plus the initial potential energy, if you're at your lowest point, is 0, equals a half mv squared, okay, which we don't know, that's something we're going to be interested in, plus mg. Well, our new height, we've worked out already, is 4/3 of whatever the length of the string is. Okay, that's the point we've been asked to examine. So we've got m common to every term here, and we're going to be trying to get v by itself. So let's start off by saying multiply through by 6, okay, to get rid of all these fractions. So that's going to give us 2's will cancel. Well, let's put it up here. There's a 6, there's a 6, and we'll put a 6 in front there. Okay, so 2's cancel here, leaving us with 3. 2's cancel here, leaving us with 3, and 3's cancel here, leaving us with 2. So we are going to get ourselves 9gl equals 3v squared plus 8. 2 by 4 is 8gl. And we've gotten rid of all the fractions. Move that over, and you get gl is 3v squared, and v squared is gl over 3. Okay, so that's going to be an important part of our calculation. Next, let's have a look at forces in our centripetal forces. So forces in are the centripetal forces. Well, our inward forces, if we come back to our original diagram, our second diagram here, are tension. And then we also have an outward force of mg cos theta. So that's subtracted. So it's T minus mg cos theta equals our centripetal force is mv squared over r. Okay, but for us that's m over r. V squared we're replacing with gl over 3. Now we also know that at the point we are interested in, this angle theta has gone all the way up here. It's become 180 minus alpha. Okay, so let's just examine what that is up here. Cos of 180 minus alpha. Probably the easiest way to do this is just straight calculator work and just say, we know for alpha is the cos inverse of 1/3. That's what we were told in the question. So let's work out what that angle is. Cos inverse of 1/3 is 70 odd degrees. So 180 minus that is 109.47 degrees. So we want the cos of 109.47 degrees, which, as it will turn out, is minus 1/3. Cos of our answer is minus 1/3. Okay, now there are neater and tidier ways to get there, but for our purposes that'll do the job. So this becomes T minus mg times minus 1/3 equals mgl, excuse me, r here is the radius of our circle, which was L. Okay, so the radius of our circle and the length of the string were the same, so that'll cancel, equals mg over 3. So that says T plus mg over 3 equals mg over 3. And of course the only way for that to be true is if T equals 0. Okay, so the string is slack. Now alternatively, another approach you can take here is to assume that T is 0 and work your way through to find the cos of this angle up here is 1/3. Both approaches are equally valid. Now I've gone on for about 10 minutes, so I'm going to do the other two questions on another video. See you then.